In module 2, what we have done is looked at kinetics and thermodynamics of reactions. So, if you have a reaction of the nature, say, okay, if we look at the rate of forward reaction, let us say we will typically write this in terms of K multiplied by some function of concentrations. Okay. The K has an Arrhenius form, and the Arrhenius form will typically look like something like A naught e to the power minus E by RT, where E is called the activation energy. Okay. So, you have seen basically if we are plotting enthalpy against reaction coordinate, we are going to start over here. This is endothermic. So, you will start over here, you will end over here. Okay. This is delta H of reaction, and this particular guy is activation energy. Okay. Delta H of reaction is positive if it is endothermic, it is negative if it is exothermic. Okay. So, this is the activation energy. Okay. This picture is strictly speaking incorrect. The reason is because this is not an elementary reaction. This reaction takes place through multiple steps. Okay. But the idea remains the same. If we are talking about a specific reaction, this will go through some kind of an activation barrier, and it will start at some point, end at some other point. Okay. The overall reaction direction can be downhill with respect to energy, or it could be uphill with respect to energy. If we are plotting in enthalpy, then we are going to get a curve like this, where everything is delta H or activation energy. If we are plotting free energy, okay, then this is usually written as delta G dagger. This is delta G of reaction. Okay. Delta G is this is what is known as activation energy. Okay. So, when you are taking e to the power minus delta G by RT, the activation energy part comes as the Arrhenius part, and e to the power delta S by R will come as the pre-exponential part. Okay. Oftentimes delta S by R does not change a lot with temperature, and that is the reason why you have your A naught, usually you have taken A naught as constant. Okay. But there are a few reactions, especially reactions that are mildly exothermic, mildly endothermic, reversible reactions, where your delta S changes with temperature, and if delta S changes with temperature, your A naught will also change with temperature, and that is where the extended Arrhenius form comes from. Okay. So, those were the things that we have done with respect to kinetics. Okay. We briefly mentioned that your f of c in kinetics has certain different forms. If it is power law, then it has a certain form. If it is not a power law, it has certain other forms. Those certain other forms for gas phase and liquid phase reactions, which do not involve solid catalysts, are what we are going to cover in module number 3. Okay. Those are looking at kinetics of various reactions, kinetics and mechanisms of various reactions. Okay. So, that is the what module 3 and module 4 are going to cover. Module 4 is going to cover catalytic reactions. Then we talked about again about reversible reactions. Let us say same example. Okay. If you are to add these two reactions up, what you are going to get is CH4 plus 2H2 giving CO2 plus 4H2. Okay. You might have other reactions of the form 2CO giving CO2 plus carbon. This is called a Boudard reaction. You might have additional reactions CH4 plus CO2 giving CO plus H2O two CO plus 2H2, I think, right, 2C, 2O, 4H, yeah. Okay, this is dry reforming, okay, and you may have many more reactions, okay. Now, delta G and delta H of reactions these are state functions. Okay. That means, if we are just to look at these three reactions, let's ignore the latter two reactions. This particular reaction is obtained just by adding the above two. Okay. So, R3 is just equal to R1 plus R2. Okay. So, you can reach R3 by first getting carbon monoxide and then reacting that carbon monoxide in with water in the water gas shift step, okay, and then you can essentially get to R3. Okay. So, you can go from CH4 and you can go this way as well, right. So, CH4 plus 2H2. Okay. So, going this way or going this way will incur the same delta H or same delta S. Okay. And because R3 is just equal to R1 plus R2, mathematically what you are going to get is, say, delta G3 okay. So, if you were to divide this by negative RT and take an exponent of that, what we will get? Okay. E to the power a plus b is e to the power a multiplied by e to the power b. Therefore, you will be able to write this as okay. So, this is something that you equivalent of this you have used in the previous lecture, where you did the tutorial. Okay. When you looked at the isomerization A, B, C, the three steps, okay, that is where you have used the same concept. Okay. This concept is very general. If I give you a very complex mechanism, does not matter, as long as delta G 5 can be represented as linear combination of delta G1, G2, G3 and G4, this particular thing absolutely works. Okay, there's no point from this point onwards you can say that, oh, this particular reaction we haven't taught, or this particular complex mechanism we haven't dealt with. It's all the same, irrespective of whether or not it is one reaction or a million reactions. And I had very quickly talked about what you will do if it's a million reactions. If it's a million reaction, you convert it into a reduced row echelon form, or you use another concept called singular value decomposition. You can use either of those two approaches. Okay. If you have done linear algebra in undergrad, or if you have seen, for example, Gilbert Strang's videos, you will probably know about the various vector spaces. Okay, that's the other approach that you can use. Okay, so you can use a very straightforward way of using Gauss elimination, or you can use something that's taught in an undergraduate course in linear algebra, which is use of null spaces and kernels. So null space of the overall matrix will give you an idea of how things are related, how the dependent reactions are related to the independent reaction. Okay. Again, what I am saying is there are various different approaches. Those approaches are not very different compared to what you do in pen and paper with your hand. Okay. It's exactly the same. It's just formalizing everything that we do with our hand in form of an algorithm that can be implemented. Okay. The other confusion people have, students have often, is what's the difference between delta G versus shorthand. We will represent this as delta Gj. What's the difference between the two? Not necessarily. Yes, good point. No, delta G. Okay, delta G is at reaction conditions, and delta G naught is at standard. Forget delta G naught. Yeah, fine. Yeah, both answers are right. Delta G is change in free energy of a particular species. That was one answer. Well, whereas delta G reaction is change in the free energy with respect to a reaction at a particular temperature or at standard temperature. What else? Okay, delta G is just a change in free energy. If you want to talk about delta G, someone also needs to specify where you are starting, where you are ending. Okay, his answer basically meant that you are starting with a particular species at some temperature and some pressure, you go to another temperature and another pressure, because of which your G changes, your free energy changes. The difference between the free energy of that species before and after is delta G. Okay, let us say it was a mixture of 4 species. You went from, say, room temperature to 400 degrees Celsius, and you went from 1 bar pressure to 5 bar pressure. Because of that change, okay, the free energy of species 1 has changed, free energy of species 2 has changed, free energy of species 3 has changed, free energy of species 4 has changed. The summation of all of those changes on free energy is the change in free energy of that particular system, starting from initial point to the final point. Okay. Let us say that in this process, what also happened is a reaction type of situation took place. So, ABCD is what you started with at one temperature, you moved to a different composition of ABCD at another temperature. Okay. How can you move that way? Okay. So, you have, so let us say we have AB and then small c and small d initially, okay, just to give you an idea that we are also and let us say this was at 25 degrees Celsius, and then we went to 400 degrees Celsius, and then we had small a, we had small b, we had large C, we have large D. Okay. And you somehow moved in this direction. Okay. Your delta G basically talks about moving from this condition to this condition. Now that involves multiple things. Okay. What would that involve? That could involve, for example, moving from here. Okay. This will be delta G reaction at 25 degrees C. Okay. And then moving to this by increased temperature. Alternatively, you can first increase temperature and you can have A, B, C, D, and then okay, because free energy is a state function, it is going to be path independent. Okay. This is what the second answer was. Delta G at 25 degrees Celsius is what, and 1 bar pressure is what we call as delta G Rxn 0 at standard condition. This is delta G of reaction at 400 degrees Celsius. Okay. Now delta G is the delta G of overall transformation going from first point to the second point. It does not matter, again, state function, it does not matter how you get there. Okay. This is, essentially the core concept, one of the core concepts of thermodynamics. Okay. Once you do your first law, second law and all that, once you start going on to into state functions, this is what you have done. Okay. So just because we are using the letter delta to represent a change, that change can happen in different ways. Okay. That change can happen. So there is a change in temperature, there is a change in pressure, there is a change in number of species because of reaction. Okay. The effect of change of temperature and pressure is captured in one aspect, the effect of only the reaction is captured in delta G of reaction. How does that come about? Okay, that comes about because you have your chemical potential as given as this, right. This is the definition of the chemical potential, your chemical potential at the ground state, okay, plus the effect of temperature and your concentrations. Okay. Now, if you are only talking about the reaction, so just the large A, large B and smaller a, smaller b, or that smaller c, smaller d, those could be 0 also. So, maybe 1 mole of A, 1 mole of B, 0 mole of C, 0 mole of D, going to 0.2 moles of A, 0.2 moles of B, 0.8 moles of C, 0.8 moles of D. If you are, for example, looking at that transformation, only attributed to that transformation, what is the free energy change? That is what delta G of reaction is. Okay. We can do that again because free energy is a state function. That means we do rest of it in one go, we only do reaction in the other go. Okay. And if look at, so delta G, so overall change in free energy is because of the ground state change, okay, and what the conditions are at the current point of time. Okay. So, let us say you are to plot free energies G, not delta G, okay, and let us say it is a reversible reaction and we are only tracking reaction coordinate. Okay. So, think about it like a bowl. and you have put a ball in the bowl. Now, bowl could be a very steep one or a very shallow one. Okay. If it is a steep one, the ball will quickly go from here and finally end up over here. Okay. Somehow it will eventually end up over here. Okay. What happens when it ends up over here? Your G is minimized. Okay. That is the free energy minimization that you would have, people would have talked about in your thermodynamics class. Okay. Or your delta G moving from this side is exactly balanced by the delta G moving from that side, which means essentially at this point your delta G is 0. Okay. What does it mean by saying that your delta G is 0? That the free energy that is because of mu naught, okay, is exactly balanced by the free energy that is because of the activities of the species. Okay. This is something that will be done in your, you have your thermodynamics class this semester? Yeah, this is something that will be done in towards the end of your thermodynamics course. Okay. We are just relating your kinetic concepts to thermodynamic concepts. Okay. And that is, now the ratio of activities is what we have chosen to call our equilibrium constant Ka. Okay. And that is where, so if we rewrite this, we will get as Ka equal to Exp that is where this comes from. Okay. If you want a more formal derivation of this, you can look at Davis and Davis book in the appendix C. Okay. You can go through that and you will hopefully you will be able to understand it. Okay. But if you did not get the last 10 minutes, that's perfectly, well, that is not perfectly okay, that is not okay. So you will have to read more in order to understand that, but you know that will not really be a hindrance in this course, so long as you understand the various aspects of how to use it. Okay. And the three things that you should carry forward with respect to for this particular course is the delta G of reaction. Okay. Delta G of reaction is the change in free energy only by tracking how the reaction proceeds. That is concept number 1. So, we are saying that we are not going to worry about change in temperature and change in pressure. If that happens, we will handle that later. Okay. Not saying we won't handle it, but you know thermodynamics, my friend is a thermodynamic expert, she will handle it. I am a reaction CRT person, so I will handle only the CRT right now. You can think in your brain like that. Okay. Again, you shouldn't, but you know you also need to get good grades in the course. So for that you can of course think of it that way, right? So that is one thing, is your delta G is if you track how the reaction progresses. Okay. If you are only sitting on that arrow that connects, if you take this reaction, okay, and you are only sitting, this is you sitting on that arrow, okay, and you are saying that you know or everything is moha maya, only the reaction is moksha and only I am going to track that moksha for myself, right. So, if you say that to yourself, you are only tracking that reaction. Okay. If you are only tracking that reaction, what you are looking at is basically delta G. Now, if there are multiple reactions that are taking place, you can hop on from this reaction to this onto this, or you can go the other way around, and those delta G's will be the same. So, that is the second concept that is relevant. The third concept that is relevant is not necessarily how you got this, but how you can use this. How you use this is K equilibrium is delta G naught of reaction by RT. Okay. Delta G naught of reaction can be at 25 degrees Celsius or at 400 degrees Celsius. So, at a given temperature. Okay. That we are going to look at, that is e to the power negative of that by RT is going to be Ka. Okay. That Ka is the ratio of forward rate constant divided by backward rate constant. Okay. And that Ka is also the ratio of product to the stoichiometric coefficients divided by reactants to the stoichiometric coefficient. What of product, what of reactants? Concentrations if in moles per liter if it is liquids, pressure in bar if it is gases, mole fractions if it is solids. Okay. So, in case of solids for most part 90% of the cases that we are going to deal with in this course, your activity for solids is going to be 1. Okay. Now, the other consequence of this is that you have your K equilibrium, your delta G of reaction has 2 parts, right. That your delta G has 2 parts, one is because of the temperature pressure, one is because of the activities. The one because of temperature and pressure is captured in your delta G naught of reaction, okay, because of activities is captured in the ratio of concentrations. Okay. Therefore, your rate constants K or your equilibrium constant capital K is independent of concentration. Okay. And therefore, this for this particular guy at equilibrium your net reaction is going to be equal to 0. Okay. So, at equilibrium R net is 0. Okay. But at equilibrium your R forward is not 0. What happens at R equilibrium? It is not the reaction has stopped. Okay. Think of it like tug of war or like a arm wrestling or whatever. Okay. Now, tug of war at equilibrium, what happens is suddenly the 2 parties have not started pulling, you are still pulling, the other one is also still pulling, but you are not moving at all. Why? Because how much this bunch is pulling and how much this bunch is pulling is the same. Okay. So, it is not that rate forward has changed, okay, or it is not that rate forward is 0, it is just that the rate forward is exactly matched by rate backward. Okay. So, if we look at this, this is non-zero. In fact, it is a positive value. Okay. What happens is it is this guy that is 0. Okay. And your therefore, you are getting your Kc is nothing but this guy does not have any concentration dependence. Okay. This is the only part that has concentration dependence. Okay. So, for this overall reaction to overall expression to be true at all times, what is needed is that rate forward minus rate backward, somehow you should be able to put it in the form rate forward multiplied by 1 minus this part. Okay. That is the 4th lesson. Okay. You will see that in module number 3 more often. Okay. And then this is the other derivation by chain rule, you can go through the other derivation by chain rule. Okay. So, what I mean by that is, let us say you have the reaction let us say this guy CH4 plus H2O. Okay. And let us say our rate of forward reaction is K okay. Then we will have rate of backward reaction as Kb multiplied by okay. But let us say the rate of forward reaction was something like this. Okay. The rate of backward reaction cannot have this form, okay, because R net is equal to R forward minus R backward. Okay. So, if you write this as K forward multiplied by P CH4 to the power 0.6 okay, this will violate this particular form. Okay. So, again what I have told you in this slide is strictly speaking not absolutely correct, it is just a shortcut. The shortcut for you, and that is lesson number 4 with respect to thermodynamics. The shortcut for you is that you should be able to put a reversible reactions R net as R forward multiplied by 1 minus 1 by Kc okay, or Kp multiplied by this. Okay, if Kc is met, Kp will also be met. You should be always be able to put in this form. If you cannot put it in this form, okay, you are going to violate thermodynamic principles. That is the last thing that you would need to remember. Okay. This is one thing that I really dislike our undergraduate books for. Whether it is chemistry or chemical engineering, throughout your undergraduate you have done reversible reactions in kinetics or in CRE only where you have treated the forward reaction as elementary, or you have treated the reversible reactions as elementary. You have never done, except a Langmuir-Hinshelwood type of thing, you have never done reversible reactions where, for example, the forward reaction has a power law form or some other form. Okay, and therefore, there is a huge amount of misconceptions when it comes to, for example, research. Students take 6 months, 8 months and so on just to get over this. Okay. So, and again in the rest of the semester you are going to come to me saying that, you know, in my undergraduate book and all. My answer to you is tough luck. I mean, I can't go and change you know, how undergraduate education is done throughout. But essentially what you do in your thermodynamics course forms a constraint to what we can do in kinetics. You cannot magically violate that constraint, right. If your ball has to fall like this, if it has enough energy it will go, if it has enough energy it will go there, but eventually where it will come and stop, it will come and stop at the bottom of that bowl. If that bowl is incredibly flat, not fast, if the bowl is incredibly flat, it might take, you know, hundreds of years to reach there. Okay, that is what kinetics talks about. Okay, but it will eventually reach there. Okay. Now, what stops the world from reaching its equilibrium? Okay, what do you think stops the world from reaching its equilibrium? We will not, none of us will be there in equilibrium. None of us, right? Our molecules are super unstable. So what stops us from going there? Again, connect to your thermodynamics. Sorry? Yes, where does the energy come from? Sun. Today, the major thing that stops us, I'm again super simplifying things, okay? The thing that stops us from going there is the sun. Another interesting tidbit of information. Oxygen is a super reactive molecule. Okay, life doesn't exist because of oxygen. Oxygen exists because of plant life. It's exactly the other way around, right? If you find oxygen on a planet, scientists need to have an explanation for that oxygen's presence. Oxygen in the molecular form. Of course, oxygen will be present in bonded form, right? One of the most dangerous things to have is a pure oxygen cylinder in labs. We usually have 20% oxygen. Okay. Oxygen is extremely reactive. Okay, so it's again it's a very odd concept, but presence of oxygen on Earth is evidence of life, not exactly the other way around. Okay, I'll have you ponder about that and thermodynamics a bit. Okay, again, a lot of these things are just oversimplified. Don't think of the simplified thing as the right thing. Simplified things are basically either for understanding or for us to be able to use it. We don't need to be an expert in thermodynamics to really do well in kinetics. Okay, but you need to have a reasonable working knowledge so that you can use all of these concepts and do the kinetics in the right manner. Okay, so that's basically the end of our module 2 and a recap of module 2 that should not have lasted that long, but that's fine. Okay, so hopefully yesterday's things were very clear. What we are going to do in the next class, I am going to start with module 3, giving you an idea of what we are going to do in module 3. Okay, so first of all, yeah, what can you look at for module 3 and module 4? You can look at Davis and Davis chapter 4, Froment and Bischoff chapter 1, okay, and also read Davis and Davis chapter 2 for some additional background information. Okay, so let us say we have the enzymatic. So the one reaction that I talked about is H2 plus Br2 giving 2HBr. Okay, and I had shown you the rate expression for this. Okay, this was in 1907 one of the first examples where the rate expression that was obtained experimentally. Okay, Bodenstein and co-workers showed a mechanistic justification for that. Okay, so it is a very interesting reaction from that perspective. Okay, so how do you get the power law type of sorry, not power law, the complex model for a free radical mechanism like this? The other mechanism is enzymatic reaction from substrate going to product called Michaelis-Menten. Okay, so how do we do this are the things that we are going to talk about in this module, and in the next module we are going to talk about, so the CH4 plus CO2 plus H2O on nickel catalyst gives this. Okay, so this would be the example of LHHW. Okay, how to get the overall rate expressions from these detailed mechanisms, we will talk about that in module 3 and 4. Okay, now whole lot of things what we are going to do in this module. We are going to break it down into reactions of the nature A going to intermediate to product, A reversibly going to intermediate to product, or A reversibly going to an intermediate that reversibly goes to a product. Okay. And we are going to use two concepts. Concept number 1 that we are going to use is to pseudo steady state, and concept number 2 we are going to use is partial equilibrium. Okay. In the next class, what we are going to do is, you remember this reaction that we kind of solved in before the first tutorial, okay, the math tutorial. Okay. The full solution is given over here, how to do it, not full solution, but full solution we have talked about how to do it. The final answers we have given over here. Okay. How we will use this in order to understand the concept of pseudo steady state is what I will start off in the next lecture. Then how do we use pseudo steady state concept in order to derive the overall mechanism is what I am going to do in the next lecture. Thereafter, we are going to use the concept of partial equilibrium. What are these concepts? How do we use them, and what results we get out of them are something that we are going to discuss in the next 2 to 3 lectures, okay, or rather next 6 lectures. Okay. What I will try to do based on your feedback is I will run these lectures as partially as tutorials, partially as lectures. Okay. So, we will upload a few things. What I would want you to do is try to look at them and try to solve them in your notebooks, and then for 5 minutes or 10 minutes, and then I will go ahead and solve them over here. Okay. So, please do read ahead, please read those 2 chapters ahead and then come for the next lecture. Okay. Thank you, see you.